Bismillahirrahmanirrahim. So today we will talk about the motion and the forces. So in the previous lectures, we discussed in detail the vectors, we discussed the cross product, the vector product, but today we start a new topic which will be the motion related topics. We start from the displacement. So displacement is the shortest distance between 2 points. So we have point A, for example, we have this point A, position A, and we have the position B. And the shortest distance here is called the displacement. If it's not the shortest distance, if we go randomly and we come to the point B, then it's called the distance, not the displacement. And we will discuss, since we talked about the vectors, and we will discuss the displacement in terms of the vectors right now. So this is our frame of reference, means, so this is the origin here, and we want to describe the motion. For example, there was a body, there was a person, for example. Initially that person was standing here and he moved from a point A to point B. We want to describe with respect to this frame of reference that how was the motion, how this person moved from point A to point B. So we have a position vector of A. So this is the position vector R1, and we have the position vector R2, and this is D. So position vector, so it means, position vector means here what is the value of A, how far is it on the y-axis and how far is it on the x-axis. This is how we discussed in our previous lectures when we were talking about the vectors. If we use the head to tail rule, we can easily add these two vectors, the position vectors, and we can get the displacement vector. In this case, so the displacement vector here is the R2 minus R1. So this is the displacement. This is how we describe displacement in terms of the vectors. And now we will come to a related topic, which is the velocity. Velocity is the rate of change of displacement. So which means that, for example, this person moved from point A to point B, and we want to, if it moved from point A to point B, it covers some distance, and we also, if we also have the information about the time, that how long does this person take to reach from point A to point B, then we will talk about, in this case, it can be described by the velocity. So velocity is generally it's the displacement covered per unit time. So to understand it better, we will take the example of a motion in 1D. Motion in 1D. So we have, for example, a car or a person or an object that was initially at time t1. So this is time t1 means it can be 0, we started from 0, and after some time the object was here at the time t2. So initially this is the position at time t1, this is the position at time t2, and after some time this object changes its position from t2 or x2 to x3, t3, and this is at time t3. And it comes back, this object comes back to, this is at t4, and this is the position vector which is at t4. And this is again, it comes back to the original position where it started. So this is the t phi. T phi is exactly at the same position, so this is x t phi. So this object was initially, for example, this might be a car, for example. Initially, this object was, so this is in a 1D, in one dimension here. So initially it was at t1, x1, so then it moved from x1 to x2 here, then x3, and it comes back here and here. So the trip is like from here and it comes back. And now we want to know how can we describe this in terms of the velocity. So the average velocity, so the velocity, average velocity, so the average velocity is represented by v, and we put a bar on it. And now we want to know what is the average velocity between time t1 and time t2. So if we look at the time t1, so time t1, the object was here, the position was xt1 and xt2. So the definition of the velocity is that is the change of the position or the change of the displacement. So t2 minus x t1 divided by t2 minus t1. We can clearly see here, since this object covered some distance, some displacement, and also has some time, so this is clearly larger than 1, larger than 0. And we take this direction as a positive x, means the x or the displacement is increasing. For example, here is 1, 2, 3, 4, 5, it's increasing in this direction. And in other direction, it's decreasing or negative. And now the average velocity between, so average velocity between t1 and t phi. So the average velocity, now we come back to this diagram here. We see here at the average velocity, we want to know what is the average velocity between the xt1 and the xt phi. So we see here that the displacement here is the 0 here, because it comes back to the same position where it started. So the displacement is 0. So if the displacement is 0, means the upper part, the denominator, is 0 here, although the time is not 0. So this is equal to 0 because the displacement is 0. And now we want to know what is the average velocity between t2 and t4. So now t2 is here. So t2 is here. So we can clearly see that the displacement between these two is the shortest distance, although the object moved from x2 to x3, but then it comes back to at t4. So the shortest distance is this one here. So we can clearly see that it's going in opposite direction of the x. So it's not equal to 0. So it is xt2 minus xt4 divided by t2 minus t4. Since it is moving in the opposite direction, it is smaller than 0. Since the velocity is a vector, so it's sign sensitive. It can be positive, means larger than 0, it can be equal to 0, and it can be smaller than 0. So when the velocity was in this direction, we can see here it is larger than 0 in the first case. In the first case that we discussed, it is larger than 0, it's positive. And in the second case, because the displacement was 0, the velocity is 0. And the third case, since the object moved from x2 to x4, the velocity is clearly negative. Now we discuss the same example in terms of the distance time diagram to understand it better. So distance time diagram. So here on the x-axis we have time, and on the y-axis we have x. So we have the time t1, and then we have time t2, time t3, and time t4, time t5. Similarly, on the y-axis we have the x1, so x2, and then we have the x3, and then we have the x4 and x, as we saw in the previous example, x4 is here. So we have the x1 here, x2 is here, x3 is here, x4 is here, and x5 is again here. Now we want to know how this object moves in the x-axis with respect to time. So to understand it better, so at the time t1, the object started from time t1, it moves from time t2, from 1 to time t2, and after some time it's here, to time t4, it's again going up, and it's coming to time t5. Now the average velocity, for example, we want to know what is the average velocity between x3 and x2. So what we need to do, we need to find this displacement here on the y-axis, and we need to find what is the time that it took. For example, here, this point here, we have the time here, and then we have here the displacement that is covered. So this is the delta t, and then we have the delta x. So the velocity, the average velocity, so the bar is telling us that it is the average velocity is the delta x, or the change in the displacement and the change in the time. So now the angle is telling us, angle here is telling us if it's positive, if the angle is positive, it means the velocity is positive. If the angle here is negative, means the velocity is negative. And now we discuss what is the difference between the speed and the velocity. So the difference between speed and velocity. So if you look at this example, so the object actually, if we draw this, the motion of this object here, so this is the started from x, this is the x. So the x1 and x5 is 0. So what actually happens is that the object started its motion from x1 here, it goes to x2, it's going up to, it's going all the way to x3 here, and then it's coming back to x4. Here we have the x4, and then it's again going up, and then it's coming to x5. So this is the complete trajectory of the this object here, and we want to know what is the difference between the velocity and the speed. If you look at the velocity as we just discussed in our previous example, when we talked about the motion in one dimension, the velocity between t1 and t5 is 0. Why? Because the displacement is 0, because x1 and x2 are the same. So if they are at the same position, means the velocity is 0. Sorry, the displacement is 0, which means the so velocity between t1 and t5, it is 0 because the displacement is 0. So the final position is positions, and the initial position is the same, so the displacement is 0, so the velocity is 0. But the speed is the distance that is covered by this object divided by time. The distance is not 0, so the distance is the length from here plus this length plus this length plus this length. For example, the total length is that is covered is 300 meters, and it covers this length in 3 seconds, for example. Then the speed between t1 and t5, so speed is 300 divided by meters by 3 seconds, it is 100 meters per second. So what we see here, that the velocity between xt1 here and xt2 here is 0 because the displacement is 0. Although the time it covers is 3 seconds, but since the displacement is 0, so the velocity is 0. But the speed is the total distance, which is not a vector, the total distance that is covered in the total time. So it is 300 by 3 seconds, so that speed is 100 meters per second. Now the average velocity is not telling us about the motion which is between these 2 points. So for example, if we want to know what is the average velocity between T1 is here, so this is not T1, this is T4, so T1, and for example T3. So what happens between these two? So what we have to do, we just take these 2 examples, the displacement between these 2 points and the time it covers. But we do not know what actually happens between these 2 points. For example, between T3 and T4 here, we can clearly see that the motion is a little bit complicated. It also went up here, but it is not telling us what actually happened between the 2 points. For example, the velocity here is 0 at this point because the angle is 0, as we discussed here. The angle here is 0. So the average velocity is not telling us about the motion between the 2 points. And for example here, between T4 and T5, the velocity or the motion is a little bit more complicated because it's going up and down. But if we take the average velocity, it will only tell us about the average velocity that's between these 2 points. If we want to know what's actually happening at each and every point, for that we will have to use the instantaneous velocity. So instantaneous velocity. We take the example of motion again in a straight line. For example, here, this is point A and this is point B. So the total distance from here to here is, for example, delta x is equal to 300 meters, and it takes, for example, 10 seconds. So if we take the average velocity, if we want to calculate the average velocity, we just need the displacement, which is from here to here. Right? For example, if the motion is, for example, the car is moving in the random direction, but still for the average velocity, so for the average velocity, we just need the displacement between these 2 points. But we never know actually what's actually happening between these 2 points. So for the average velocity, we will just divide this displacement by time, and it will give us the average velocity. But if we want to know what's actually happening between these 2 points, we have to take a shorter time. For example, this is, for example, it took 10 seconds from here to here, and if we take the time that delta t is equal to 0.1 second, which is much smaller than this one. So if the time that is taken by this object to move in this path, if this is shorter, it means in this short time the object will also cover a small distance here. If it's a small distance here, so if we take this even smaller, and which is approaching to, for example, 0, then it will tell us, for example, almost it's 0, then we can calculate the velocity at each and every point. And that's called the instantaneous velocity. And instantaneous velocity means that the velocity at each and every point. So that's why, so it's mathematically it can be written. So instantaneous velocity is the limit when delta t is approaching to 0, and the x is t plus delta t plus minus t divided by delta t. So what it means is the same equation as we discussed for the average velocity, but we just, so this is the in the bracket in the subscript. So this is the final velocity. So this is the final velocity minus initial velocity divided by the time that it takes. But now we are interested in the velocity and each and every time, each and every moment in time. So this equation now means that if we take the small portion of this path, for example, in the x, for example, if we take a smaller time, means we are taking the small portion. If it's approaching to 0, means we take extremely small portion of the time that it takes to cover a distance. And it will, since if the time is smaller, it means the distance that the object will cover will also be small. It means that the velocity that is calculated using this equation will be at each and every point. For example, if it's smaller time, for example, 0.1 second, it's very much smaller than the total time, for example, that it takes. So it will give us the velocity at this moment in time, and also small positions here. So when it's approaching to 0 means that the time that it takes is extremely small, and this is called the instantaneous velocity. And its instantaneous velocity is telling us, it's giving us the information about the motion of the object at each and every point. Now we discuss the acceleration. Acceleration. So acceleration is the time rate of change of velocity. So a change of the time rate of change of velocity means, so we have the acceleration, so the bar here again means the average. So we have the final velocity, that means the change of velocity, the final velocity, and t1 here. So this is, we can also say that this is the final velocity minus initial velocity, and this is time t2 minus t1. And we can also write here that the change in velocity divided by time. So this is the average velocity. So since we can see here that this is the velocity is here, the unit of the velocity is meters per second, but we have another second here, so multiply by second, so we have the meters per second square. So so this is the unit in the SI unit system. And now we have the example of we can take the example of the gravitational acceleration. So gravitational acceleration, which is represented by g. So it's the acceleration, it's equal to the 9.8 meters per second squared. So what it means that if, for example, we have a ball, for example, there is a gravitational force which will cause the gravitational acceleration. So this is the g, and this is, for example, the ground. If we let this apple or this ball, let it go in the influence of the gravity, the initial velocity will be 0. So the initial velocity means at the time t equals 0, means 0 seconds, velocity will be 0. At time equals 1 second, after exactly 1 second, the velocity will be 9.8 meters per second. This is what it means, that after 1 second, the 9.8 meters per second will be added to the velocity of this object, for example. And after time 2 seconds, the velocity will be 19.6 meters per second. So 9.8 is added to the 9.8, and we will have the 19.6 meters per second. And at time equals to 3, the velocity will be 29.4 meters per second. So 9.8 meters per second means that after 1 second, the 9.8 meters per second velocity is added to the velocity here. So the velocity will be increased by the rate of 9.8 meters per second. And now we take the example of the bouncing ball. So we have, for example, we throw a ball. For example, we have here, this is a ground, and then we throw a ball which is going towards the earth with the velocity of 5 meters per second. It is bounced back in upward direction. This is plus 5 meters per second. So the plus and the minus is representing the direction. For example, this is our x, positive. So when we go up, we have the positive direction. When we go down, the direction is negative. And now we want to know what is the acceleration in this case here. We can clearly see here that the velocity was 5 meters per second. Here minus 5 meters per second means it was going in the downward direction, and after some time it's going in upward direction. So there is a change in velocity, but the change of the velocity actually happens when it hits the ground. So we want to know what was that time, that the impact time, and that time is extremely short in this case, because when it hits the ground, that it will immediately comes back, and that time is, for example, here in this case is minus. So this time is the 100th of a second. So the acceleration is change in velocity minus divided by change in time. So in this case, we have the phi of final velocity is phi minus phi divided by 10 raised to power minus 2. So this impact time is extremely short. So we will have the here 10 divided by 10 raised to the power minus 2. So we will get 10. So we can clearly see here that the acceleration here is extremely large because the impact time was extremely short. So in this case, so when we threw a ball towards the earth and it comes back with the same velocity, but the impact time was extremely short. When it hits the ground, that was extremely short, and that was 10 raised to power minus 2 seconds here. And the acceleration when we calculate it is 1000 meters per second. That's extremely large acceleration. When we compare it to the gravitational acceleration, it's 9.8, and when we compare it to this one here, this is extremely large. That's why whenever we throw something, it hits the ground, for example, even with the modest velocity, we throw something hard, for example, a cup, for example, it will break. It will break because the acceleration is extremely large. Whenever something breaks, it's because that the acceleration is extremely large. Here, whenever something, for example, during the accident when the car is moving, when it hits the other car or something else, because the impact time is extremely short, the change in velocity in the very short time, the velocity changes in extremely short time, and because of that the acceleration is extremely large. That's why there is a lot of damage in the accidents, or whenever we throw something hard, for example, we throw an egg, it will break because the acceleration is extremely large, and the acceleration is large because of this small impact time. Now we said that the acceleration is the change in velocity with respect to time, since the velocity is a vector. Since the velocity is a vector, so change in velocity could mean that the change can be in the magnitude or direction. For example, the examples that we discussed here, in this case, in these cases, for example, here the magnitude is changing. The magnitude of the velocity is changing, that's why we have the acceleration. But if the magnitude is the same, but the velocity is, the magnitude is the same and the direction is changing, there will also be acceleration. And that's acceleration, for example, something is moving in a circular path. So we will have the acceleration which will be here. For example, the velocity of the magnitude of the velocity means the speed of this object is constant, it's not changing. For example, the terminal speed is 5 meters per second throughout this trajectory, but we can clearly see that at each and every point the velocity is changing. So even if the direction is changing, we will have the acceleration. In this case, we have the centripetal acceleration. We will discuss the centripetal acceleration later in this course. So we discussed about the instantaneous velocity, that the instantaneous velocity is telling us about the motion at each and every point, and we take this, the time, the changing time when it's approaching to zero. When it's approaching to zero, for example, here, this time, for example, when it's approaching to zero means that it's giving us the information about the motion at each and every point. Similarly, for the instantaneous acceleration, so instantaneous acceleration is the same. So we have the instantaneous acceleration. So we have the, when the limiting case here, when the delta t. So I will not go into the detail, but it's the similar thing. It's just giving us about information about the motion of the object, so that we will get the acceleration, for example, here at each and every point, and for that purpose we use the instantaneous velocity. Now we discuss the velocity time graphs for different cases. Velocity time graph. So the first case that we discuss is that, so this is the time and this is the velocity here. So whenever we have a straight line, for example, here, so this means that whenever, so the time at the passage of, with the passage of time, the velocity is constant. For example, this is, for example, 5 meters per second here, so it remains the same throughout the time. So which means there is no change in the velocity. That means that if there is no change in the velocity, that means the acceleration is zero. And we discussed in our, when we were talking about the vectors, we said that if we multiply the time, multiply by the velocity here, it will give us the distance. So this is the area under the curve. So area under this curve here is distance that's covered by this object. And now we take the second example. So again, we have on the x-axis we have time, and on the y-axis we have the velocity. So whenever we have a straight line, so a linear case, so what we see here with the passage of time, so with the passage of time, so this is the increasing time here, so 0 for example, then it's increasing here, and the y-axis we can also see with the passage of time the velocity is increasing. So if the velocity is increasing means it's constant, the straight line means it's constant. So velocity is constant. And in the case of constant velocity, we can use the average velocity. The average velocity means, so average velocity here is the 0 plus, so the initial velocity plus the final velocity. The initial velocity we can see here, it's 0, starting from 0, and we use the average velocity. Divided by 2, it's 1 by 2. And the area that is under the curve here, we can clearly see here. So this curve here, so this is the distance that is total distance that is covered. So we can see here, this is a triangle, and in a right angle triangle. So the area under the curve is the distance that is covered. So the formula for that will be the area of the triangle. So area of the triangle, so area of a triangle is equal to 1 by 2 base multiplied by height. So base here is the time, that's delta t means the time here, and the velocity. So this here is the velocity. So this is 1 by 2 v cross t. So this is the distance that is covered. And the slope of this curve is also the acceleration here. In this case, the slope is the acceleration. The third case that we discuss, when the acceleration is changing but not constant. So what we see here as the passage of time, with the passage of time, so this is the velocity. So with the passage of time, the velocity is increasing, but it's not with the constant rate. It's increasing. It's kind of exponential here. So acceleration here, since the velocity is changing but not constant, so the acceleration is increasing. So in this case, we will have to use the concept of the instantaneous velocity. The instantaneous velocity, because we can clearly see that the average velocity will not tell us what's actually happening at each and every point. So for the instantaneous velocity, as we said, the slope is giving us the acceleration. So if here we take a tangent at each and every point, for example at point A, this will give us the instantaneous velocity at point A. For example, if we take the slope here, it will give us the velocity at the instantaneous velocity at that particular point. And now we will take an example in which we will try to understand the velocities, the concept of velocity and the concept of acceleration that we just discussed. So the example here that we take is, this is the time axis, and this is the velocity. So this is the velocity. So this is 5 seconds. So this is in the seconds. Here we have 10 seconds. We have here 15 seconds, and here we have 20 seconds. So here we have 10 meters per second, so the velocity is in 10 meters per second, and here we have the 20 meters per second. So this is what actually happens. So with the passage of time, the velocity increases from 0 to 20 meters per second. Here is the 20 meters per second in 5 seconds. So at the 0 seconds here, the velocity was 0. After 5 seconds, the velocity here is 20 meters per second. And for the next 10 seconds, from 5 seconds to 15 seconds, the velocity remains at 20 meters per second. And after 15 seconds, the velocity again reduces to 0 in the next 5 seconds. So we want to know that how much distance is covered by this object or this car here during this time, whatever information that we have. And we also want to know, since the velocity is changing here and is constant, what is the acceleration in this case. So this is, for example, point A. We have the point B, we have the point C, then we have the D. So we can see here, this is the making a triangle. This is the point. As we just discussed in our previous example, that the distance covered is the area that's under this curve. What we see here, this is the making a triangle here, this is a triangle, then we have a rectangle, and then we have a triangle here again. So if we measure, if we calculate the area of the triangle plus the area of this rectangle and this triangle here, we will get the distance that is covered in this time. So the distance that is covered here is the area of a triangle which is A, B, and this is F. A, B, F plus the area of a rectangle. This is B, C, E, F. B, C, E, F plus the area of triangle which is C, D, and F, which is C, D, and F. So it is equal to 1 by 2. We have the velocity multiplied by time here. So we have the 1 by 2. So here the velocity is the height here, and then we have the base is the time, and this is the area of this triangle, plus the area of this rectangle is the time multiplied by the velocity. So velocity multiplied by time, and again plus the area of the third triangle here is the 1 by 2 height multiplied by the base. So base is again time and the velocity. So this is plus 1 by 2 velocity plus time. So if you put the values, so 1 by 2, 20 multiplied by 5. Why? Because we can see the velocity here is 20 and the time that it took from point 0 to 5. So this is 5 plus, and then we have, it takes 10 seconds from here to here. So we have 10 multiplied by, and the velocity remains the same. So we have the 20 plus 1 by 2. We have the, again here, the 20 multiplied by 5. So the velocity, the height here is the velocity, which is 20 here, and then we have the 5 seconds from here. If we multiply this thing, calculate, we will have the 290 meters. So this is how we calculated the time. The distance that is covered in this case here. So what we did that we calculated the area of this triangle, then the area of this triangle, and area of here in this triangle. Now since we calculated the distance that is covered by this this object in this example, now we want to see what is the change in the velocity and the change in velocity with respect to time. So what we see here between the point B and C, the velocity remains the same, it's not changing. So if the velocity remains the same, if it's not changing, that means the change in velocity is 0, which means the acceleration is 0. So between point B and C, the acceleration is 0, because the velocity remains the constant. And between, so this is for the 10 seconds here, so the acceleration is 0. Between point A and B, for this 5 seconds, initially the velocity was 0 meters per second, and then after 5 seconds the velocity is 20 meters per second, means the velocity increased, which means that there is the positive acceleration So there is a positive acceleration here. In this case, we can see that the velocity here for the final 5 seconds, between 15 seconds and the 20 seconds, between these 2 points, between the point C and D, the velocity decreases from 20 to 0. It means the acceleration decreased, and this decrease and decreasing acceleration is also known as the deceleration. So if we calculate, so here the acceleration is 0. If we calculate the acceleration here, the change in velocity, so this will be the final velocity minus 0. This is the initial velocity, and we take the time here, so we will get 4 meters per second square. And here we will get A equals minus, because final velocity here is 0 here, and it's decreasing, so we will have the 4 meters per second squared. So now we talk about the equation. So we talked about the motion, types of motion and terms associated with motion. We talked about speed, we talked about acceleration. So acceleration, I will just write speed was speed, which velocity is meters per second. Acceleration was final velocity minus initial velocity divided by time. So we had velocity was time, distance covered per unit time, and acceleration was how fast the speed is changing per unit time squared here. This is initial velocity, final velocity minus initial velocity divided by time, and this will give us the acceleration, and the acceleration is how fast the velocity is changing. So now we talk about, so we have here the, we talked about this, figure here. First, this axis here is the speed, so here we have the, just concentrate here, we have the 0 speed here, and then we have the initial speed here, and then we have the final speed here. So 0 speed means it's increased from, for example, 0 to 50 meters per second, and then 100, for example, meters per second. We don't define it, we just have the initial speed here, and then we have the final speed here. On this axis we have the time axis here. So from here it's 0, and then the time is increasing. And now we have a body here which has the initial velocity. We have a car, for example, here, which has the initial velocity here. Initial velocity is here, but with this after some time the velocity is increasing, and then it's after after t time, t, which is a variable, its velocity is vf, which is final velocity. And the slope of this line here is the acceleration here, acceleration here. So now you understand what's this whole graph about. So we have the 0, so just just explain it again. We have a body here, its velocity is initial velocity here, and after some time, this is the time axis, after some time its velocity is final velocity, which is vf. Now the slope of this line here is the acceleration. Which is A. What is the slope of this line here? Slope, as you know, slope is this side of this triangle, and then we have this side of this triangle. So we have the slope is BC divided by, so BC, so this line, so the slope of this object, so acceleration equals, we have the, so this is the general from the geometry, basic geometry, BC divided by AC. Here, so we have the acceleration equals, so now what's the BC? BC, this part is completely BD minus CD. So BD minus CD is this side, right? It's simple. So BD, complete line from here to there, from this point to this point. If we subtract from this point, this line, this part, we have this part BD. So we can write BD, so BD is this one here, minus CD, right? So we could replace BD by BD minus CD, right? So it's the same thing, just another words. So we have then AC, oh sorry, AC. Now, so acceleration or the slope of those objects. So this is the slope of the line, right? This is the slope of the line. What is BD? BD. So BD is 0 to final velocity. So we can just replace VF minus, and what is CD? CD here is VI. And what is AC? AC. So it's same as this time here. Now we move this T to here. So we have AT equals VF minus VI, or VF equals VI plus AT. So this is the first equation. So this is the first equation of motion. So this is VF final velocity is equal to initial velocity plus AT. So this is, you need to remember this in this first equation of the motion. These will be used in the later lectures. This is important. So the first equation is, so now we write here VI plus AT. So from this figure, we derive the first equation of motion, which is here. So what was the first equation of motion? Final velocity is equal to initial velocity plus AT. So this is important. You need to remember this velocity, this equation here. Now we derive the second equation of motion from exactly the same figure. But for that we need, so the total distance covered. The total distance covered is the area under this curve. What is the total area? The total area under this curve is the area of this triangle here. You can see this is a triangle here, and then plus the area of this rectangle here. So the total area, so the total distance is the total area of the rectangle here, which is OACD here, plus triangle here, the area of the triangle, which is ABC here. Right now, first we derive the area of the rectangle here, which is the area of the rectangle here is this side. Rectangle, just concentrate on this triangle here. So triangle, area of the triangle is this side multiplied by this side. So this side is OA, which is here, OA, and then OD. What is OA here? Initial velocity, because this is OA multiplied by this AT. So this is the area of the rectangle from here, this area of the rectangle. So total we need, but we need the total area under this curve. So we have now AT. So this is the area of this rectangle here, and then now we need the area of this triangle. So the area of the triangle here, this ABC, that triangle here. 1 by 2, half multiplied by AC. AC means AC this side, and then BC. So when we put the values, these values here, which is the time, and then we have AT there. So now what we do, so we have here the area of triangle, a triangle here, and then we have the area of rectangle there. So we take the area of this rectangle plus this area of rectangle, we put these two to this equation here, which is here, the distance covered, total distance covered. We just put these two to that equation number A. So this is the coming from the equation number A here. And then we have here the distance covered is this equation here, which is the second equation of motion here. We just derive the first two equations for based on that figure here. Now we need to write here. So we have first derived first equation, and now we have distance covered V is equal to VIT, initial velocity multiplied by T, time covered, plus 1 over 2 AT square. So this is the second equation here. So we have the first equation, now we have the second equation, now we come to the third equation. So we derived the first two equations of motions. So this one was the first equation, and now we have the second equation here, and we have, as we said, we have three equations of motion. So we again come to this figure here. We will derive the third equation of motion also from this equation here. So in the previous, the second equation of motion, what we did, we considered the total area, but we divided it into this rectangle and the triangle here, and then we derived the third equation of motion. For the third equation of motion, what we do, we take this is the third equation of motion here. So we take the total area under this curve again, which is the total distance covered, which is S, which is represented by S. So this is the total area, total distance covered by this object when it's moving from here to here. I mean, when the initial velocity is its initial velocity, and it reaches to the final velocity, and then given in this given time. So the total area is OA. OA is here, multiplied by plus BD. So the BD is here, and then multiplied by OA. So this is the total area under this curve. So previously what we did, we took this area of this triangle and then this one. But for the third equation, we just write the total area of this of the area under this curve. Now what we do, we take this 2 to this S here, we just shift this one here. So we have 2S here, but the remaining is the same OA. But to simplify this equation here, we just multiply both sides by BC divided by OD, which is the acceleration or the slope of this object. So which is BC divided by OD here, so which is the acceleration or the slope of this curve here. So what we do, we multiply this slope or the which is also acceleration. So we'll multiply by both sides, so which is here, which is the same equation, but we just multiply to both sides, which doesn't make any difference. What we do here, so when we multiply this thing, these two are cancelled here. So the remaining equation here is the same here, 2S, and then this what we multiplied, and then this part, and then only this OD. This OD is cancelled. Now we have finally this equation here. We just insert the values. For example, for this one, BC, what we said is the slope of this line, which is the acceleration. We just write the A, which is A stands for the acceleration. And then we have OA. OA from here to here is the initial velocity. And then we have the BC. BC, you can see here BC is the same as this final velocity. We have plus final velocity, and then BC here is initial velocity minus final velocity. This is final velocity. So what do we see here? A plus B multiplied by A minus B is the same equation here. We just use the same formula there. We have the 2AS equals to final velocity squared minus initial velocity squared. This is the third equation of motion. We just write it here. Third equation of motion is 2AS equals final velocity minus initial velocity. Now, so we have the three equations of motions. Why do we calculate? Why do we need them? So for example, these equations relate the initial velocity, final velocity, acceleration, time, distance. You see all the variables, all the terms that are associated with the motion. So if we have this equation and we have certain given parameters, a certain value, for example, we have the initial velocity, we have the acceleration of the object, and we have the time, and we want to know the final velocity. We can just calculate the final velocity. Similarly, if we have all these things and we want to calculate the initial velocity, we can calculate the initial velocity. If we have the initial velocity and the acceleration and the time covered, we can calculate easily the distance covered by this object which is moving. Similarly, we have another equation. So with all these equations are used to calculate different parameters there. So in your homework, there are some